Okay, so next part of recurrent neural nets. This is about the latest state-of-the-art approaches, and I'll talk about two of them, but a bit quickly. The first one is an improvement over the LSTM, named the phased LSTM, and the other one cares about speed of these mechanisms, okay? The first one, recap LSTM, and I want to depict the following thing. In this equation, imagine we have no input time step, okay? Now we're not setting input information. What would happen? Forget gate would be acting on the cell state anyway, at every time step. There's no deactivation of this cell, of this gate, sorry. So what it means is it would keep forgetting and forgetting whatever it wants to forget without any input information, so we wouldn't filling up the cell state again. So these have a quick forget rate. Although it can retain long-term dependencies, we can do it maybe a bit better to retain longer dependencies. Okay, this is the idea, like expanding this long-term memory. And we do so by placing an additional gate in two parts of the cell. So this was the classic cell. Now we're placing this timing cell, timing gate, that says whether the cell is activated or not by means of a periodic signal. And the periodic signal is the following one. We have this signal with period t and phase shift s, and an active cycle range of within the period. Okay, so whenever the cycle is active, the cell is active and it lets information flow happen. Okay, this is the idea, and those three parameters are self-learned again. So we have more parameters to learn within the cell, but for a positive purpose if we have enough data. And the way it works is we have three states of that gate. First, when we are in the first part of the cycle, of the activated cycle, we let information flow. Then in the second part, we make it decay. And finally, we block. So this alpha parameter is for training purposes, okay? This is a leak factor that's called to let gradients flow when we're training. Because if we block the information for those time steps, there's no gradient flowing. But during test, imagine, during test means forward predictions. This is just blocked, okay? So in those areas without the yellow signal, there's no information flowing, and these are the equations of the activations of the cell. Just to have, you have to keep in mind that we have like clock signals, like in a digital circuit somehow, and these clock signals are telling the cells whether to update or not. Okay, you can see these spikes here that are activated for every cell. We have many cells here, some cells, like 1, 2, 3, 4, 5 cells. And here we have different time clock periods for every cell, one clock period. And then we have the linear input increasing, and it basically updates itself just when the clock hits, okay? Every cell happens to be acting like that. And this is the nature of this phased LSTM. And why? Well, and the results, this was presented 1-2 months ago in a very important conference here in Barcelona, and this is the state-of-the-art results it gets, beating the LSTM in convergence speed, because you can see the accuracy during training per epoch. Yesterday you saw what epochs are, and you see this high-speed convergence it has compared to other LSTM variants, the oldest one, without this self-learned clock information to activate or deactivate. And this is another example of the loss mean square error learning for another task, where you can see that the PLSTM learns quite faster than the LSTM approaches. And the important fact here is that why this is converging faster. Maybe it's because it's learning when it has to be activated to be strict about what happens, what happens to be important. And second, the long-range dependencies it gains, it's larger long-range dependencies, it's because whenever the gate closes at any time step, imagine I'm in a certain time step, I close the gate and the information, the cell state is preserved perfectly, okay? Nothing's flowing in or out of that cell. 20 time steps afterwards, maybe that cell happens to be activated, which means flows go in and flow goes out, and the cell state's modified. But when the gates open, we have a fresh copy of whatever happened 20 time steps away. So this is like freezing some time steps selectively that the network chooses to do so, and we have them intact where in LSTM it didn't happen to be like that because there was nothing blocking any activity inside the cell. But here we are freezing the cell and reactivating it afterwards. Okay? And now just to finish with the latest architecture, this one works a bit differently because we don't have these fully connections everywhere as you've seen like in an RNN, okay? This is about 1D convolutional neural nets, and Elisa yesterday introduced them, and I wanted to do this introduction to go to the causal convolutions because they are the basics of our next and last architecture. So imagine we have this sentence of 8 words with a vector per word of 100 dimensions, okay? We arrange all them together like this. We basically put them like on the floor, and we have this sequence length and 100 dimensions matrix, right? And we want to apply a kernel of width 3 of 1D convolution. Imagine I basically take all this and I just pick up one, okay? One, but there are 100 constantly, okay? But just pick one dimension to depict it easily. If we do the 1D convolution without any padding, what we get is out of the length 8 sequence with this 3 by 3 kernel, the final is the 6 length sequence. This is from Signals and Systems. Then if we add the padding, as Elisa said, we have that we respect the input length. But what happens here is that we can do the padding just on the left side, and what will happen is sample 1 will only depend on sample 1 of the input. Sample 2 will only depend on sample 2 of the input, and so on, which means the convolutions are causal in this case because they depend only on the current time step or the past, but not any future. Okay? We're forcing that by setting the padding just on the left side. Enough padding. In this case, it's kernel width minus 1 zeros. Right? So this is the basics for this next architecture and last one, which is the Quasi-RNN. It's called Quasi-RNN because it's not a full RNN as you've seen before. Here what it happens is, remember the LSTM? We had some linear projections, these red blocks, like the cell activation, dot products. These are dot products, okay, by those matrices you've seen. And here we have the blue blocks, which are the forget and input and output gate element-wise multiplications to activate whatever was required, okay, these blue blocks. So this this has a problem, as every time step is dependent on the activity that happened before. This happened to be slow architectures. Okay, during training and even testing for 1,000 words sentence, well, that's not an unlikely thing, but for 1,000 periodic signal or whatever we may have of time steps, large amount of time steps, these get quite slow. And on the other hand, we have convolution neural nets that make this convolution that Elisa said yesterday, and we can perform them in parallel. So all this happen to be in parallel, parallelized in our system, okay? And the max pooling can also be done in parallel. It doesn't matter the order, as I've said, okay? They have no notion of order, but we can try to mix up the best of both worlds, and that's the Quasi-RNN, where we have first a convolutional stage, like here, but with causal convolutions, the one I show you, because we want this causality to be respected as we're dealing with sequences, and we want to imitate somehow the RNNs. Okay, this is why causal 1D convolutions are required, and then we want to apply some pooling that's lightweight, okay, but that imposes the ordering like this did. And first there is this convolution operations where we have the sequence we've seen before. Time steps in that case was 8 words, so length 8. And the feature dimension, as every word was a 100-dimensional vector, 8 times 100. And then we basically process this activation of making the convolving filters with this X vector, with the 10H. And this computes the activation of all the time steps, okay, in parallel. We can do so in parallel. If we have the sentence, we compute all them in parallel. Not like before with the LSTM that we had to go time step by time step. Same happens when we want to compute gate values. We make the same operation with each gate's kernels, and we apply the sigmoid function to make this behavior of a switch between 0 and 1. And we have all computed in parallel the hardest task operations, these dot products, okay? And if you basically limit the kernel width to be 2, so if you limit this to be 2, what would happen is that these equations arise. And these, you could say, are quite similar to LSTM equations because they depend just on x of t and x of t minus 1, okay? So this is the kind of way of mixing up both worlds, of having the convolution compute all the activations, and then we apply whatever pooling we want. So we can compute, like here, forget gates, or output gates, and input gates. We can choose what gate to apply, okay? There are many flavors published in the paper of the original authors. And we can do just the forget gate of the previous time step, plus the inverse of what's been forgetted, the inverse quantity, letting input. We can do forget and output pooling, or we can apply the input and forget and output, which is basically what the LSTM did. But you can see the similarity with LSTM equations, although what happens, so this is the recurrent operation, where the slowly place comes in, okay? But it's not that slow as in LSTM, because here, the dependence of every time step is just about an element-wise product, not a whole projection per activation, okay? This is the idea. All projections has been done in parallel before. Pooling is done just element-wise product. And some final main ideas to be kept regarding RNNs. They are very good to process sequences, so whenever order matters, try to apply them. Generally, LSTM and GRUs perform similarly. I've told you I would give you some clue or thought about what to use. It's interesting to try by yourselves in any task you choose which perform better or not, but people claimed in some publications regarding some different tasks that they perform similarly, okay? But if you have lots of data, maybe go for LSTM, as it has more flexibility with more parameters. If you have less amounts of data, like, I don't know how to give a rule of thumb, but if you have huge amounts of data, LSTM may be better, if not, GRU, okay? Like, for 2,000 samples, I would go for GRU, for instance. Training samples, I mean. If you want to process very long sequences, maybe PLSTM is the solution, and if you worry about efficient architectures to have high-speed computation, q-rnn is the way to go, maybe, so you can give it a try as well. And yeah, finally, thanks for the attention and sorry for the rush.